we have a topic about what we call engineered wood products. So basically artificial products made out of timber. We see some example here on the desk. After I will pass on to you so you can touch it and see better how they look like, how they are made of. So with this lecture we will basically start introducing these engineered wood products, and we will spend a bit of more time on two types of products which are, I would say, the most important one at the moment in our country, in Europe in general. So what we call glue laminated timber, so this one, I can just give it to you so you can start touching and have a look. And what we call cross-laminated timber. Even this one, it's a bit heavier, but perhaps it's better to see. So cross-laminated timber. So what we are going to do, we are going to highlight what are the advantages of this material relative to solid timber, so some timber, what we were discussing yesterday basically. Then the manufacturing process, so how are they produced? And then we will show some examples of real structure made from glue, just to see what is the potential of the material in the end. So we will start by answering a number of questions. First of all, why use engineered wood products? Why it's appropriate? Do we need to use this kind of products here? What is glue laminated timber, legno lamellare incollato in Italia? Why laminate timber? So what's the advantage to basically cut wood in small pieces and then glue them together? Why has glue laminated timber got better mechanical properties compared to some timber? How is glue manufactured? Produced basically. We will talk about the strength classes. So also for glue we have to basically classify the material. Of course, we need, as a designer, we need to know the strength. So the characteristic strength. Remember yesterday? No, it's no longer here. The formula we saw yesterday. The design strength of timber is equal to K mol modification factor that accounts for moisture variation, for moisture content, and load duration times characteristic strength divided by partial safety factor. So we need to know the characteristic strength also for glue. So also for glue, like for some timber, for reinforced concrete, we will have to consider different strength classes. So we will talk about strength classes for glue. Then again this other material, cross-laminated timber, sometimes you will find it denoted with CLT, cross-laminated timber, this kind of abbreviation. Sometimes you will find with XLAM, so XLAM, okay? Those two ways of denoting this kind of material. It's cross-laminated timber. In Italian we would translate like legno lamellare incrociato. Also, legno lamellare incrociato, also this one is glue. So, legno lamellare incrociato, incollato. Now we don't say incollato because the other one, the linear one, is legno lamellare incollato. Quindi legno lamellare incollato, legno lamellare incrociato. Both of them are glue. Then we will talk about another material that we cannot find in Italy at the moment, which is called LVL, laminated linear lumber. In Italian, it has been translated into microlamellare. This is not used in Italy, but is very much used in countries such as Finland, the Scandinavian country, and also in France, and also in Germany, and more recently in Switzerland. Plywood. And also this one, I can give it to you so you can start having a look. Plywood is what we call in Italian compensato strutturale. It's this other material here that I give it to you now. So, compensato strutturale, plywood. Similar to what we use for the boats sometimes. What is in Italian is called compensato marino. Same kind of stuff. And then other kind of panels, now unfortunately I don't have this one here, MDF, which is medium density fiber. In Italy, in Italian, I don't know, it's usually considered like MDF, usually find that just this abbreviation. It would be pannello di particelle. OSB, oriented strand board. Also this one is pannello di scaglie, di legno. And then particle boards. Particle board is what we know as a truciolare. Also in Italia is usually known as OSB. It would be pannello di scaglie orientato, but OSB, also in Italia, say OSB, then you should understand what we are talking about. Particle board, truciolare. This one, all of us know what is truciolare. Okay? And then we will conclude by showing some examples of glue lamp structures. Now we start by highlighting, by pointing out what are the disadvantages of soft timber, of solid timber. So, we have already an extended data about the timber itself. And we saw that there are some disadvantages. Of course, there are several advantages, but also some disadvantages. First of all, if you want to use soft timber or solid timber, of course, the size of your structural member is limited. So we can't really build a beam long 40 meters, for example, but even if it was shorter 10 meters, we are struggling to find out a cross-section, for example, let's say 20 by 60. To find a cross-section 20 by 60, you need to have a very big log. And even if you find a very big log, you remember after you cut each cross-section, 20 by 60, what you have to do after, before you can use it. Suppose you can find this 20 by 60 cross-section from some big tree, you cut it, and then you use it immediately. Now, what are you supposed to do? You have a good structure. Once you cut out of the wood your timber, then you should dry. So dry at 20 by 60 cross-section basically will take a huge amount of time. So nobody would be able to dry. Then you would have to use it green, and then you would expect after some months some cracks to occur, very big cracks. And then the creep will be very high. Remember yesterday, creep will be K depth would be 2, and so on, even more than 2, because we will see if the timber is not dry, you need to add 1 to the creep coefficient. So if you use it, for example, inside, you have, let's say, you're using a heated environment, the K depth coefficient will be 0.6, but you can't use 0.6. You need to add 1 because the timber is green, so 1.6. So you get a huge creep coefficient, lots of problem. So I would say that for a certain size hole, it's definitely better not to use some timber, because then you can encounter lots of problems. So the first drawback, large size of structural member limited by the size of the tree. Second problem, only straight member can be produced, while instead we know that the demand from the architects is more and more to have curved structure. Funny shapes. You can have a funny shape with a straight member. Yes, you could, but then you need to do a piecewise beam, you need to cut small sections, then you need to glue the section together in order to get a curve, which is not a real curve, it's a piecewise beam. But of course the architect don't like piecewise beam, you usually get the real arch. So, another problem, only straight members. And then if you remember yesterday, actually the day before yesterday, no, it was 2 days ago, it was on Monday, when we were talking about the strength of some timber as related to the strength of clear specimen, so small specimen. If you remember, there was a table showing that the strength of the clear specimen, 80, 40, and so on. And then when we go to the soft timber, this 80 will become 40, so there was a strong reduction of strength due to the influence of the defects. So in the end, we have a material, some timber, which on average is very good, would be very good, but due to the knots, we have to basically downgrade the strength due to the knots. Reduce reliability. Remember the plot with the clouds of points showing module of elasticity and strength for 1,000, actually was 10,000 specimens. Big cloud showing that there is a huge scatter of results because the timber is a natural material. Okay? And last but not least, anisotropic behavior that we saw last week. Of course, an anisotropic behavior, very good in one direction, very bad in all the other direction, is a problem. It's a problem because in some cases we cannot avoid to load the timber in the wrong direction, which is the direction perpendicular to the plane. So the idea would be that theoretically you should always try to load the wood parallel to the grain, but this is not always possible. For example, in the joint region, in a joint, you have some secondary stresses perpendicular to the grain. Those stresses, usually we ignore those stresses when we design with concrete and with steel because the material is isotropic. So those are secondary stresses, lower than the primary one, but since the material performs exactly the same in the two directions, we don't care about that. Instead, for timber, unfortunately not. The secondary stresses may cause failure because they act in the low strength direction. Okay? It's clear so far? Any question with this summary of 5 point problems with some timber? So the idea is that to solve those problems, we invented this engineering wood products. Yes? Affidabilità. Affidabilità. Okay? So this engineering wood products, if you want, is the answer of the timber industry to those problems. How to get over those kind of problems. You can see here a number of beam type engineering timber products. So we need to make a distinction between linear members, so members that are mostly used for beams and columns, and plate type members, so members that are mostly used for two-dimensional structure like walls and panels in general. So which are the most important ones here? Glue laminated timber, we already have one specimen, so this one basically. This is by far the most important in our country and all around the world. And then in our country often you find this glued solid wood, which is basically 2 or 3 pieces of wood glued together along, you see, the vertical surface. 2 or 3. In Italian it's also called bilama if there are 2 pieces of wood, or trilama if there are 3 pieces of wood. This is quite fairly common in our country. In our country, for example, when we design a roof, and you need not a roof for a house, so you don't need huge cross section. You could also use solid wood, some timber, but it's much more common to use this. Why? Because it's better to use this for cross section, for small cross section. We're talking about, for example, 14 by 16, 14 by, yes, this kind of section, 20 by 30, quite small. Why is it more common to use this material? Because it's much more stable. It is the pieces of wood first are dried and are put together, the material is much more stable. You don't have problem with cracks and creep and so on. Okay? So we said glue solid wood, glue laminated timber, and then laminated veneer lumber is this other material that I showed you before, not very common in our country. And then you see these other products here, not so common. For example, this one is a kind of artificial eye section made of wood, where you can see there is the 2 flanges are made of LVL, and the web is made of OSB, OSB, this one, is this kind of product that sometimes you find to fence a building site. If you look at a building site, sometimes they have a kind of, even here you can find in this kind of building, if you go just close to this part in here, there is a building which is covered with this kind of material, OSB, oriented strand board. Just want to see. So plate type engineered timber products, medium density fiber, we'll see later, it's the kind of product we use mostly from the furniture industry. It's mostly used for furniture, particularly for kitchens. Plywood. Plywood is used for, we will see, for floors and walls, perhaps not so common here in Italy. Particle board, floors and walls, also this one, it's a low strength material, so it's more used, it's not so much used in the construction industry. And then you have crosslamp. This is the most important one. Crosslamp, the one that I showed you before, so again this one, this is by far the most used timber products, plate type timber products right now in Italy. And then cross-banded NBI. There you can see some kind of solutions that are not even in English. They have their original name in German because they were produced in Austria, they're produced in Austria rather than in Germany, in this other country here. So we start with glue laminated timber, again, this kind of material, this, or again, this one. Glue laminated timber. Now, how is it produced? So it's a solid wood member manufactured by gluing smaller pieces. So we cut the tree into planks and we glue these planks together. You can see here a photo and a drawing. So the idea, as I said before, again, we cut from the tree some planks. Usually those planks are 40 to 50 millimeter thick and 1.5 to 5 meter long. So we cut the planks. Then we need to join them lengthwise. Unfortunately, here it's very clear today, so you can't see very well. So we should try to pull down another curtains. You know, if some of you want to try to pull down this curtain, this way we can have we can see a bit better. Thank you. So the idea is that these planks are only from 1.5 to 5 meter long. Our member usually is longer, so those planks need to be joined. You see, lengthwise. So head to head. So they are joined using the so-called finger joint. Finger joint is called because you can see the wood is cut in small fingers. Those fingers are glued together. Why is it cut in this way? Because in order to increase the strength, we need a long surface. So we have more glued surface, okay? If we were to do a scarf joint, so a scarf joint would be something like this. So if this is the plank and this is another plank, with a finger joint, the other possibility would be to have something like this. Scarf joint, but in this case you see the surface is much shorter compared to this. In this case it's much easier to get failure of the glue than in this case here. So we join them lengthwise with a finger joint, and then this is called lamination in the end. So this long, basically those planks are joined lengthwise. We obtain at the end a plank which is as long as the beam. So for example, for a 20 meter beam, we obtain a plank which is 40 millimeter thick, perhaps 200 millimeter wide, and 20 meter long. This is called lamination. So those lamination then needs to be glued together. So now we need to have some glue between the different lamination. Okay, so these are glued planes. So why laminate timber? First reason to basically produce glue laminated timber is to produce larger dimensions and specs than what is possible on some timber. We can get up to 2 meters, so we can get cross section up to 2 meter high. Usually they are 20, 30 centimeter wide, not too big, so the width is 20 to 30 centimeters, and length up to 40 meters. Theoretically, we could also have members longer than 40 meters, but then the problem will be the transportation. This product here, as you can imagine, is not produced on the building side. It's produced in a manufacturing warehouse. Okay? And then it needs to be transported on the building site. So beyond 40 meters, the transportation is a problem. Then, other good reason, freedom in the choice of geometrical shape, straight curve and aesthetic appearance. So in this way we can make architects happy, because you can see here we can have very nice shape, curved shape, variable cross section. See different kind of shapes, curved member, other interesting shapes, lots of curves. And you see here can also be curved in the horizontal plane, not only in the vertical plane, but also in the horizontal plane. So we can get something which has very good aesthetic appearance. Other photos of big structure made of glulam dark beams. And then another good reason to produce glulam is to improve the mechanical properties, strength and stiffness of the products. In this table here, you can see a comparison between, this is New Zealand glulam, but we can have the same result also using European glulam. So basically the idea is that I have a certain type of timber. For example, in New Zealand was Fragiacomo. Here in Europe we use Corse. I cut the planks. So from the planks I get, well, planks, yeah, let's say that the saw timber out of radiata pine or out of spruce, you can get a bending strength of, let's say, 18 megapascal. Then if you use the planks out of the same material, the same grade, you glue them together, rather than using separately, you glue them together, you can see here you can get this glulam here, you can improve the strength from 18 to 19, from 18 to 22. So there is an increase in strength just due to the fact that we have cut the wood in smaller pieces and we have made a new product by re-gluing the same pieces. Now we are going to understand why there is this increase in strength. So why there is this larger strength? So I try to repeat the concept. I consider one tree. I cut the wood from this tree. I compare the strength properties of the wood used as a normal wood and the strength properties of the glulam obtained using the same wood. The two materials have different properties. Just because I have cut the tree into smaller pieces and re-glued together, I get a better product than the original wood from the tree. Why is that? First of all, because of the controlled manufacturing process. So to produce the glulam, in order to make the glue going off, like I said yesterday, so to basically glue well, I need to dry the timber, I need to grade the timber, I need to do some texting, stiffness testing. But the most important reason is the fact that by cutting the tree in small planks and gluing them together, the defects, particularly the knots, are reduced. If you remember the principle that we discussed on Monday, is it better to have one larger, only one big knot, or to have more smaller knots? What was the answer? More smaller knots are better. Okay? So the idea is that basically, suppose that I have a piece of wood with a very big defect inside. In this case, of course, the strength of this piece of wood will be significantly reduced compared to the strength of the clear wood because of this huge defect. Now, suppose that I want to slice down this piece into smaller pieces, so very small thickness, like this here. This would be not glulam, this would be LDL. I'm getting to the number. So an original prismatic piece of wood with a very large knot. And then I slice down in a number of pieces, and this number of pieces after that, they are re-glued together to repeat the same piece. Why do I get a better product? Because when I reglue again the same pieces, I reglue those pieces with a random order. I'm not going to reglue exactly with a not in exactly the same position. Because of course I'm not going to slice down a piece like this, I'm going to slice down the whole tree, basically. And then I'm going randomly to reglue together the pieces. So what was originally a knot going through, it becomes, you see, in one slice you have the knot here, which is now only as thick as the thickness of the piece. So before was, let's say, 30 millimeter large knot. Now if I slice in 10 pieces, I have 3 millimeter knot here, then 3 millimeter knot here, then another 3 millimeter knot here, and so on. So this knot has been basically spread out the volume. So rather than having only one large knot, 30 millimeter thick, now I have 10 knots, only 3 millimeter thick, which are not, of course, in the same position. They're spread out the volume. So according to that principle that we said before and we discussed yesterday, this product is much better than this, because the knot is much smaller. So this is the reason to laminate timber, so to produce glula, and particularly LVL. With LVL, the strength is much higher compared to the strength of the original wood. We can say that with LVL, we get a product that is as strong as the clear material. So basically, if we slice the wood in 3 millimeter veneers, in the end, we can get that the influence of the knot is negligible. So it's like having no knots at all. Okay?
At the end, I cut the lines of wood to reduce the influence.
The defect, exactly. Yes, yes. Yes. It's mostly for the knot. So this is, we saw different type of defects. This production method is mostly to reduce the influence of the knot. No, all of them. See here? If you have a big knot in your timber, once you, let's say your trunk you have a number of knots. Like if you remember, there was a photo showing. This is a vertical cross section of the trunk. Something like this, if you remember. So here you have the fiber are going this way, so this will be a knot. The fiber going this way, this will be another knot. Once you basically, we will see later, but this knot here is basically cut in this way. Here there is like a shape. So the whole trunk becomes like a roll of toilet paper, to understand. So it becomes this way. So this one becomes a veneer like this, which is 3 millimeter thick. So the whole trunk goes through this plate, and at the end it becomes a very long veneer, 3 millimeter thick. So this knot here, you will have it here, then you will have it here, and so on. After this long veneer, you cut in small pieces, and then you again assemble them. So they glue them together. So the knots are randomly spread out throughout the body. They are not again rebuilt in the same position. Okay? So rather than having one large knot going through, now you have knots which are at maximum 3 millimeter thick.
Infatti io dicevo, siccome il knot agisce con profondità, cambiandolo è come se riducessi il grano cartaceo.
This is if you cut this, then you have this one, which is only on this first veneer, only 3 millimeters. Then the second one is here, because when you glue it, then again it's a random process. You know, the chances that they are aligned is very low. Okay? It's clear this concept. This is another crucial concept to understand LVL, glue, and so on. Very interestingly, if we draw now the probability density function, remember in reinforced concrete design we'll learn about the probability density function. Probability density function of a random variable. It's a curve showing the probability to get a certain value, for example, of strength. So if you draw here the probability density function, this Gaussian normal distribution function of the strength for graded timber, you would get a bell-type curve like this. So if you compare now the trend of the probability density function for Luna, you will see that this curve is higher and narrower. What does it mean? If you remember what we studied in 2 years ago in reinforced concrete design, what does it mean that the probability density function is narrower?
Less dispersion.
Less dispersion, less scatter of results. It means that the material is more reliable the narrower the curve. In fact, for steel, if you remember, for steel you have a very high curve, because steel is very reliable, very reduced scatter of results. And then if you put here LVL, you see even higher. So as you move from graded timber to glulam to LVL, you move from a material which is characterized by lots of dispersion, lots of scatter, to a material which is much more reliable, LVL. Interestingly, if you compare the mean value of strength in these 3 cases, as you can see, the mean value of strength is almost the same. So, on average, some timber, glulam, and LVL have more or less the same strength. Well, LVL is a bit higher, but not a lot. But of course, since the curve is narrower, the standard deviation is smaller, and therefore the characteristic strength is completely different. So the characteristic strength of LVL is significantly larger than the characteristic strength of glulam, and the characteristic strength of glulam is significantly larger than the characteristic strength of graded timber. And of course, we know very well that when we design for any structural material, what counts in design is which quantity? Characteristic strength. In our formula, remember yesterday, K mod times Fk characteristic strength, not mean strength. So this is the reason why, again, we are ready to spend money to produce, of course, because glulam and LVL, we have to do much more work to produce that. We have to cut the wood, glue, and so on. So they cost more than some timber, but you have a much better result in terms of strength. It's clear this concept. This is another concept that I hope it is very clear, because it's on this concept is based all these kind of products that you can see on the market. So I would like, do you have any doubt about what we have discussed so far? Everything fine? Okay. Another good reason to produce glulam is to match the lamination quality to the level of stress. So to produce what is called combined glulam. Legno, lamellato, collato, combinato. Instead that homogeneous glulam, legno, lamellato, collato, homogeneo. What is the difference between these 2 materials? Well, the idea is that, of course, when we create a straight member, very often we use the straight member for a beam. And for a beam, we know quite well that if we assume, like we did, if you remember, we said that conventionally we will design a timber member for bending, assuming a conventional linear distribution in tension, in compression. Remember, assuming this kind of conventional bending strength. Remember what we said, theoretically we should consider a limit plasticization in compression, but this would make it too complex, so conventionally I consider just a purely linear elastic distribution of stresses, like you learn in mechanics of material. So Navier formula, okay? So this means you see that if you have this distribution of, we said we use this for bending, mostly for beam. Beam is mostly subject to bending. So usually the governing design criteria is bending, not shear. And then if it is bending, we know very well that the maximum strength demand is on the outer fiber. So more stress compressed zone and more stress tensile zone. So the idea is that since I can buy on the market plugs characterized by different strengths, in order to optimize my material, I could say, okay, I spend a little bit more money for the plugs that I put on the outer lamination, which are the most stressed ones. So I use higher strength plugs in the outer fiber, in the outer lamination, and lower strength plugs in the inner lamination, in order to obtain what is called combined glue. So combined glue, for example, is made of plugs to be T20, so I could do something like this. I say, okay, here, these two, T20, these two, T20. Just remind you, T20 means that the strength, characteristic strength, tensile strength is 20 megapascal, and here in the middle, T15, for example, the lowest strength. This way, I'm going to use the most, let's say, the stronger classes, also the most expensive one outside, where I need more strength, and the lower strength classes inside, where I need less. Okay, so this is called combined glue laminated, called combined glue. Another good reason to produce glue laminated timber is the stability of shell during exposure to moisture. Why is that? Because, as I said before, in order to be able to glue the lamination together, the plant needs to be kiln dried to 12% of moisture count, 12-14% of moisture count. So since I need to kiln dry all the plants, the product that I have is already basically dry and is less sensitive to moisture content variations. Other important advantages, very important when you do prefabricated members, we have a dimensional accuracy thanks to the control production process. So basically everything is produced into a factory. So in the end we have that the dimensional the size are very accurate. This is very important in a prefabricated structure when after it comes to put those prefabricated members together. You have to have a low tolerance because otherwise you may get some problem. You may not be able to connect them together. Okay? Okay, one important thing, often you get that during the drying process, and so on, you get some cracks in the planks. So it's very important that those cracks are oriented in such a way that if you have to use the glue in outdoor condition, the water doesn't penetrate inside. So if you see cracks like this, if you expose in outdoor conditions this cross section, it's clear that during a rainy day, the water of the rain will just penetrate inside. Once the water penetrates inside, it's very hard for this water to get outside, and they may lead to some proper durability. You will have a specific lecture on durability with my colleague, Dr. Ciometta. So this we will discuss later about this. But I think it's quite obvious that since wood a hygroscopic material, it's much better to avoid that the water goes inside. What can you do? You can do by orienting, you see these cracks in the other way. In order instead to make it easier for the water to go outside rather than to go inside. And to protect with the head here, with a cover, to protect the upper parts of the beam. So the solution on the left-hand side should not be used, obviously. Here you can see different shapes of beams. Of course, the idea is that glue laminated beams cost less if they are of standard size. Standard size is straight direction, it's a straight shape. But then you can see often you use also this kind of taper beam, where you optimize basically. You have the higher cross section, where you have also the higher bending moment. This is double taper beam, and you can see here also pieces of arch. So it's basically this is a portal frame. Half of the portal frame can be done this way in order to avoid the joint here, and also glued curved members. Curved members, of course, are more expensive than straight members. So, of course, if you need to do curved members, very nice, very lovely, that's lovely, but just remember it costs a little bit more. You see also the different pieces of glue lab can be joined together having a very big finger joint like this. So here, for example, you have this half portal frame here is made of 3 pieces. This is one piece, another piece, and another piece. Those pieces are joined together using the finger joint. Of course, again, the gluing of this part here will be done not on the building side, but in the factory. The idea, just as a general concept, is that all the gluing should always be done in controlled environment. So never on the building side, always in the factory. Okay, so if we need gluing, the glue should be always done in the factory, because it's a difficult process, let's put it this way. It's not taken for granted that when you do the glue will be effective. And of course, very often you have no way to check this, so it's very important that it's done in controlled environment. So this is basically the manufacturing process. You see here, we start from the boards. So basically, we have already, in the saw mill, we have cut the tree into the boards. Then the boards are graded. So this is all an industrial process here, basically. So the boards are automatically graded and stiffness tested. Then the boards are cut into the length from 1.5 to 5 meters. Then they are profiled to get this, what is the finger joint, so to get basically this kind of profile. Then you see the boards are glued. So the different boards are glued head by head by putting some glue here. Sometimes some of the boards, some of the lamination are tested in order to check that the glue is effective, so the finger joints work well. The idea is that the finger joints should have a strength not lower than the strength of the lamination itself. So the finger joint should, actually the glue joint should be stronger than the wood of the board. Then you see we have the glue application. So this is so here first we put the glue here, we compress, and we keep for some time in order to allow the glue to go off here. And then later on, if this is the lamination, later on the glue is poured on this surface, on the lateral surface, on the top of the board, and then of course another board is placed above, and so on. You get to the cross section. You can see here. So glue application, the different laminations stacked one above the other, and then we have a final assembly, clamping and curing. So in order, again, for the glue to make the effect to go off, you need to apply some pressure, and then to leave it there to cure for some hours, one day. once the cross-section of the beam is ready, so once the glue has gone off, then we have a trimming, sanding, and finishing of the beam. You can see the same process with some photos. We start from the logs. The logs are cut in sawmills, the segarie, into 40 to 50 millimeter thick planks, with lengths in the range 1.5 to 5 meters. Then the planks are kiln dried, because the adhesive requires the moisture content of wood not to exceed 15%. So we need to dry all the planks in order to have the moisture content not higher than 15%. Then after drying, if you remember, we will have some distortion. So we need to pre-plane the plank. So basically, if you want to have a final cross-section of 200 by, let's say, 40, you need at the beginning to have a larger cross-section, maybe something like 120 by 45, by 46. Because after once it dries, it distorts, and then we need to pre-plane again the plank in order to go. So we need to take away some of the material to go again to a prismatic, undistorted plank. The plank then needs to be strength graded. So automatically you see the planks go through this device, which is applying 2 concentrated force, so 4-point bending moment. It measures directly the deflection, and with this formula here, you can calculate the module of elasticity. So if you know the applied load and the deflection, you put in this formula and you work out the module of elasticity of the beam. If you remember, there is a correlation between the module of elasticity of the beam and the strength of the beam. Not very strong correlation, but there is a correlation. So in this way, we can do what we call strength grading, actually machine strength grading. Then, the end of the planks you see are cut off and profiled for finger joint. The adhesive is applied on the two surfaces, and the planks are pressed together for at least 2 seconds. You can see here one plank, another plank. The finger joint you can see here because it's covered by the glue. And then with these devices here, we apply a force, a compression force. As I said before, as a part of the production process, we need to control that the production process works well. And so some of the lamination randomly, some of the finger joints randomly are basically tested in bending. This is a destructive test. So in this case, we are not only measuring the deflection, we are actually breaking the finger joint. As you can see here, this is a press. This is a 2-point load, so this one goes up until the finger joint breaks. The outcome of the test should be that the failure, hopefully, will occur in the wood rather than the finger joint. Okay, or if it occurs in the finger joint, it should be anyway higher than the strain class of the wood itself. Okay? Okay, now the continuous section is cut into laminations of the required length and stored for at least 8 hours to ensure the curing of the glue. So we need at least 8 hours to make sure that the glue of the finger joint will be cured. Then the glue is applied and the lamination is applied on the surface, now the big surface of the plank, and the laminations are pressed together. You see there is a pressure between 0.5 and 1.2 Newton per square millimeter. You see this is the continuous lamination already with the finger joint here. So we apply the glue top and bottom, and then all these laminations are stuck together, and with this jig here, basically, we are pressing together the lamination. So basically we apply a cross-section, we apply pressure this one. In order to ensure that the gluing of these surfaces will be good. So you see here there are basically two very long, two very long glulam beams on the edge, pressed together with these jigs here, pressing device. And here instead you see 1, 2, 3, 4, no, sorry, 1, 2, 3, 4, 5, 6 arches made of glue laminated timber pressed together during the gluing process. Okay? So the glue lines are kept under pressure to control climate. So climate should be controlled 20 Celsius degree, 65% relative humidity for at least 6 hours. So the members should be there for at least 6 hours before the clamps are released. And the beams are start ready for finishing. What does it mean finishing? You see that this section here doesn't have a very nice appearance right now, so we need to plane again. So this is a planer, and with the planer you plane on the surface. And at the end you see there are some holes, for example, there is some holes for connections. For example, this beam has to be connected with dowels or with bolts. You need to pre-drill to create the bolt for the hole for the bolts. And then often there are some coatings are applied on the beam itself. Those coatings could be just for architectural reason. For example, the architect may want to paint the wood using, for example, white color or something different, or could be also to protect the wood from the environment. So it could be some kind of sealing agent even to protect the wood from the bottom. This, for example, is an application of this. You see here, this is a part of probably a 3-inch arch. So this would be the actual inch made of steel. And so this steel plate is connected to the wood using glued-in rods. So using basically barre di acciaio incollate. So there are some holes here going inside the wood. And there are some rods, threaded rods. And from this vertical point here, there are some epoxy resin which are basically pressed inside. And this resin is going to basically fill in the gap between the hole in the wood and the threaded rod. So if you look, you have a situation like this, for example, 1, 2, 3, 4, 1, 2, 3, 4. So inside this hole you have your bar, the threaded bar. And from here you have some holes, vertical holes, where you inject the epoxy resin. So the epoxy resin are going to fit in this gap here and to glue the threaded rod to the wood. We will talk about also, discuss later on about how to design this kind of connection here. Important general rule is that finger joints should not be, let's say there are anyway a weak point, they should not be aligned on the cross section. So the idea is that the finger joints should be on different cross sections. In terms of strength classes for, let's say, glued products, there is a new regulation that has been produced a few years ago, this EN 14080, where there is a very clear definition at the beginning about glued-in products. So you see, we start from number 1, which is the basic component, is the board. So the board is the basic component of all these different products. So a board, we said before, a board is between 1.5 to 5 meter long, and in terms of thickness, we say 40 to 50 millimeter thick. So the board can be used for structural finger jointed timber. So just the board is just finger jointed together for a product like this, or can be used for glue laminated products. Number 4. And the glue-laminated product, you can see, can be glued solid timber, this one, what we were saying before, dilama, trilama, and glue-laminated timber, glue-lam, this one. Glue-lam could be finger jointed, like this one, glue-lam with large finger joints. So there are the small finger joints between the boards, and also there is a very large finger joint between these two members. Then this number 8 is called block glued glue-lam. What does it mean, block glued glue-lam? As I said before, the boards are not very wide. Usually, when you order a board, you never exceed probably 20 centimeters of width, 20, 24 centimeters maximum. So if you need for your structure a larger width, you have to produce different glue-lam beams and then to glue the beams together like here. So, in other words, for a glue-lam member, what is, let's say, what should I be too big is this width here. This width is the width of the board. Let's say maximum 20, 24 centimeters. But if you need more, if you need, for example, 40 centimeters, the idea is that you produce two members like this, and then you glue on the surface here. So, for example, in this case, you see we have a very big cross-section, 4 glue-lam members that then have been glued along these vertical surfaces. So we have, if you want, 3 different gluing processes. First, you have the gluing of the finger joints between the lamination. Then you have the glue of the lamination between lamination, and then you have the glue between different glue-lam members on the side in order to get what is called this block glue-lam. Okay? And then you see, so we have different regulation. For this one, you have the regulation EN 15497. For this, you have the regulation EN 14080 for the glue-lam. And then there is another regulation for cross-lam, this EN 16351. So cross-lam, you see here in this column here, cross-lam is a plate-like product. In this case, you have again the finger joints between the lamination, but then you have a gluing between lamination arranged in a perpendicular direction. So you can see here in the cross-lam, we have a layer of boards running in this direction. Then the adjacent one is running in the perpendicular direction, and then the next one again perpendicular to the first or parallel to the first one. And also in this case, the different cross-lam parties can be finger jointed along the whole cross-section. So this one is called cross-lam, cross-laminated timber. And again, the idea of cross-laminated timber is like similar to the idea of glue-lam, except that in this case the laminations are arranged, the adjacent laminations are arranged perpendicular to each other. Now, talking about strength classes of glue-lam, there is this regulation EN 14080. Now, in design, we need some properties. When we design a glue-lam member, we need to know some of the properties of the glue-lam. So what does this regulation tell us? The characteristic strength, stiffness, and density property of glue-lam timber shall be verified either. So there are 3 options. One option, from classifications from layout and lamination properties. So we will see that basically, in order to get the regulation basically suggests some typical configurations of glue-lam members, and if the producer of glue-lam members comply with this typical configuration, he already knows that this glue-lam will be assigned to a certain strength. Okay? So a producer of glue-lam have different ways to produce a certain strength class of glue-lam that after is needed to the designer, of course, to his design structure. First way, he basically look at these tables, which I'm going to show now, where the regulation set typical configurations for which the strength is a certain value. This is the first way. The second way is to use some formula. So calculation taking into account the cross-sectional layout, documented property of boards. So you can do an explicit calculation, we will see later. Or he can do full-scale tests. So he can take can produce his glue lump and then do test to failure. Of course, the third bullet point is the less attractive, because it means that he has to have some machines to do the testing, and it's not so simple. So usually, the first two bullet points are used. Now, if you read through, characteristic strength, stiffness, and density properties may be declared by reference to a strength class according to a table we are going to see now. Usually, when we talk about glue lump, the strength class is denoted by GL. GL means glue laminated. So GL, and then there is a number. The number, so GL, for example, 40, means that 40 is the characteristic strength in bending associated with this strength class. So GL 40 means that I have a glue laminated timber that has a characteristic bending strength of at least 40 megapascal. Okay? Then there is another letter. So for example, GL40 can be C or H, either C or H. So C means this is combined glue lump. Combined glue lump was what we were saying before, different strength of the boards along the cross section. Or H means homogeneous. In the case of a homogeneous glue lump, the boards are all the same strength classes. Okay? So, just to memorize, let's say that this one the one where we have different strength classes of boards, this is combined. So this will be GL, for example, 40C. Instead, when we have the lamination all with the same strength class, this is GL40H. So homogeneous and combined. Okay? Okay, another important thing. Characteristic bending strength shall be valid for glue lump with a depth H of 600 millimeter. And so the reference depth for glue lump is 600 millimeter. And the lamination thickness of 40 millimeter. So the standard glue lump is 600 millimeter deep and made of laminations, boards, 400 millimeter thick. Eh? 40. What did I say something wrong? So the whole cross section must be 600 millimeter deep. And the lamination shall be made of 40 millimeter thick boards. So, if the thickness is less than the thickness of the lamination than the 40 millimeter, then the bending strength will be multiplied by this factor here. Then we have some other details. Now we don't want to read everything because perhaps it's a bit boring, but so some information provided here. So now let's instead understand these three different methods to produce glue lump of a certain strength class. We said that the first method is basically just to comply with some tables. Let's see how it works, how this method works. So first of all, we need to use boards which have been classified for tensile strength. So the boards, basically, you see here there is this table showing the kind of board that we should be using in our glue lump. So T class of boards, T8 corresponds to C14. Remember, T are the boards that have been classified by tension, and C are the boards that have been classified by bending. So T8 means that the board has got a characteristic tensile strength larger than or equal to 8 megapascal. C14 means that the board has a characteristic bending strength this time larger than or equal to 14 megapascal. You remember, then by now it should be clear that tensile strength is lower than bending strength. You remember what we discussed on Monday. So at T8 corresponds to C14 because 8 is a tensile strength, FT0 L cap, so in this case it will be the tensile strength of the lamination, characteristic tensile strength of the lamination. You remember what does 0 mean here? Why it is written FT0 LK? So F strength. 0 means that, yes, longitudinal direction will be 0 degree with respect to the graph, so parallel to the graph. T is tension and is lamination case characteristic. So T8 means characteristic tensile strength of at least 8 megapascal. Mode of elasticity at least 7 gigapascal, and then characteristic density of at least 290 kilogram per square per cubic meter. So this regulation said, first of all, we need to use boards which are classified and comply with this table here. Okay? So the producer is going to buy some of those, some boards that are classified will have a stamp showing this kind of strength classes on the board itself. Then, strength of the finger joints. The required characteristic value of the flatwise bending strength of finger joints, F, M, J, K, in lamination shall be taken from table 2 or 3. If the finger joint is 15 tension, okay. So the idea is that the producer of cross-lamp has to ensure that his body is able to produce finger joints which have a certain bending strength. Okay? So, in order to ensure that the finger joints that he produces are a certain bending strength, you need to control continuously the production by doing this test that I showed before. So randomly, every 100 lamination, to take one lamination and to test for bending the finger joints in order to check that the value obtained, the characteristic value, is higher than the limit value provided by the regulation. Now we're going to see that, if, for example, if you want to obtain a GL plus GL20C, which means a glue laminated, a combined glue laminated timber beam with a bending strength of at least 20 megapascal, the regulation tells that we need to use some value of the tensile strength of the board and then some minimum value of the bending strength of the finger joint. Okay? You can see here outer zone of lamination, outer zone, and inner zone of lamination. So let's see here, for example. We said before, example, GL20C. So we want, let's say that the designer has required for a certain structure the use of glue lamp GL20C. How can a producer make sure that the glue lamp is producing is GL20C? He checked in this table here, you see here GL20C. Outer zone of laminations, intermediate and inner zone of laminations. So outer zone of laminations are this gray area. Inner zone of lamination is this white area here. So the table tells us that the outer zone of lamination, we need to use boards of strength class T13 at least, with a proportion of 2 times 33%. And with a characteristic value of the bending finger joints of 21 Newton per square millimeter. In the inner zone of lamination, at least strength class T8, proportion 34%, and finger joints of at least 18 Newton per square millimeter. So if you want now to basically to represent the cross section, in this case, what we should be doing? Okay. Outer zone of lamination. So outer zone of lamination are those shaped one. Proportion 2 times 33%. So if this is, let's say D, this should be 0.33 D, and this should be 0.33 D. Inner zone of lamination, 34%. So this should be 0.34 D. Okay? Then, strain classes in the outer zone of lamination here, T13. In the inner zone of lamination, T8. T8, T13. What does it mean, T13? If you go back, T13, you see here, means 13 characteristic tensile strength or 13 megapascal. Or, could be also a C22. So T13 or C22. Instead, T8 could be also C14. So the producer could buy either timber planks that have been classified in tension, so they are classified T13, or they have been classified in bending, but C22. Because this doesn't mean that the C22 is better than the C13. The larger value of the number is just related to the fact that in the classification in bending, 22 is the bending strength, while instead 13 is the tensile strength. We already learned that bending strength is higher than tensile strength. So basically, because as I said, the same class. One is classified in bending, the other one is classified in tension. Okay? And then we said, so T13 or C22 for the outer lamination, T8 or C14 for the inner lamination. And then, so you have to buy those planks, and then you have to ensure a minimum strength, bending strength for the finger joint that it is going to produce. So the minimum strength you see for the outer lamination, T13, is 21 megapascal. So this would be F, M, J, K. So F, strength, bending, joint, finger joint, characteristic. This should be greater than or equal to, we're talking about now, we said T13, so T13, 26 megapascal. For the inner lamination, F, M, J, K, greater than 18 megapascal. And for the outer lamination again, F, M, J, K, greater than 26 megapascal. Okay? So a glue lamine that complies with this requirement can be classified as GL20C. Then we see there is another table providing from GL20C all the strain profile that we need in design. It's clear? Just a remark, you can see that for G20C there is only one possibility. So we just need to use this configuration. Of course, then it depends on the size of the beam. Here could be only 2 laminations, 2, or it could be more than 2, it could be also 4. 4 and 4. Okay? Or 3, 3 and 3. 1, 1 and 1 is not okay because it's too little. So we start from 2, 2 and 2, 3, 3 and 3, 4, 4 and 4 and so on. For this configuration here. Okay, it's clear? What I was saying before, for other strain classes, for example, you see here for the GL28C, which is the most common in design, you have different possibilities. You have 1, 2, 3, 4, 5, 6 different configurations. So, sorry, 6 different possibilities to achieve the GL28C. What is the difference between the different possibilities? You see that in one case, you use lower strength board, T21 instead of T22, for example, but with so T21 instead of T22 with a proportion of 2 times 17%. Instead here you have T22 2 times 20%. So let's see the difference between the first, for example, GL28C. In this case, we have to use we use the lower value of strength in terms of the board, but we have a more extended outer part. So in other words, the difference is that in one case the first possibility is something like this. D 0.25D, 0.25D, and here we use T18. Here T14. This is one option to get the GL28C. And then there's another option. Let's check the last one, so we see that the extreme, what is the difference between the extremes. So the last option, GL28C, we have, if this is D, 2 times 17, so basically T22 T22 and T13. So basically, the producer can choose to get, in order to get the same GL28C class, he can use whether to have more plants outside, which are little strength, T18, or less plants outside, which are however stronger, T22. Depending on the value of the strength classes available for the boards. Okay, so both configurations leads in the end to the same strength class. In both cases, just remind you, the producer anyway have to comply with this minimum value of the characteristic bending strength of the finger joint. So for this reason, you have to have a way to make an internal control, so to do some tests, experimental testing, to ensure that the characteristic value of the bending strength of the finger joint has a minimum, the minimum required value coming from this value. Okay, it's clear how it works. Then of course you have another table for homogeneous. For homogeneous, much simpler. For example, if you want to get a CL28 homogeneous, you just have to use T18 boards. So all the boards must be T18 with a characteristic finger joint of at least 36 megapascal. As I said before, there is a table showing all the strength profile for a given strength class. So for example, GL20C has a bending strength characteristic of 20 megapascal, tensile strength parallel to the ray of 15 megapascal. Sorry, yes, tensile strength perpendicular to the ray almost 0.5, as you can see, and then all the other properties, compression, parallel perpendicular to the ray, shear strength, shear and torsion, rolling shear, remember we discussed about rolling shear, and all the different quantities. Okay? So when you do your structural design, basically this is the table that you need. From here you select a certain value of glulam strength, a certain class, and from the class you have all the profile. This is combined glulam, and this is homogeneous glulam. Okay? This was the first way. I said before there are 3 methods. This was the first method. The second method is basically to use some formulas. So verification from cross-sectional layout and properties of both and finger joints. So the strength and stiffness properties of homogeneous glue-laminated timber shall be determined from the strength and stiffness property of the lamination using the formula given in table 6. So you see here, you are a producer, you produce a certain type of glulam. As a producer, you need to know the characteristic tensile strength parallel to the grain of the board and the characteristic bending strength of the finger joint. So these two quantities, FT0LK, characteristic tensile strength parallel to the grain of the board, and FMJK, characteristic bending strength of the finger joint. The first FT0LK can be taken from the classification of the board. The second one should be provided by the producer based on the test, on this experimental test that we're going to do on the finger joint. If you know those two quantities, you see there is a formula to calculate the characteristic bending strength of glulam, FMJK, using this kind of empirical equation. And then, once you know this, you can find also all the other quantities that you need for your design. Okay? The third way, as I said before, was to do just experimental testing. In the reality, the most common ways are the first two. So, the table, the tabular procedure, the first one that we went through is the most common one. Okay, any question about this? Okay, if there are no questions, then we move to the next product, which is called cross-laminated panels. So cross-laminated panel, as I said before, is usually abbreviated with CLT or sometimes with XLAM. Both of them abbreviation of the same kind of material, cross-laminated timber, or in Italian we say legno lamellare incrociato. So the cross-laminated timber can be regarded as the extension of the glue laminated beams to two-dimensional structures. In this case, okay, these are prefabricated solid slabs obtained by laminating together lumps of timber. Unlike glulam, adjacent layers are arranged at the right angle. So the adjacent layer boards are glued at the right angle. Glue or nails can be used. I can tell you that 99% of the case, glue is used to glue together the board. There are some production of nailed cross-lamp, but the properties of this nail are not so good as the one with glue. Production of cross-lamp, we start from spruce boards with thicknesses varying from 17 to 27 mm, width from 160 to 200. They are first kiln dried to 10-12% of moisture content and plain. Then they are machine graded, checked for defects, and finger jointed in length, like we saw before for a cross slab. Then they are assembled in layers. And just remind you, the adjacent layer at the right angle. And they are cross-fluid with melamine Miura formaldehyde fluid. From 3 layers up to 11 layers. So we can have the 5 layers is the most common one, perhaps this one, 5 layers. But we can have a layout from 3 layers up to 11. You can see here, this is the spreading of the glue. And then the other bolts are placed on top. And then we have to apply pressure to allow the glue to go. So, for the pressure we can use vacuum presses. So, towards the end of the course, we will try to organize a visit of the cross-lab producer that we have in Pescara, but close to here. And then you will see he has a vacuum press like this to produce the glue panel. The best presses, however, are the hydraulic presses that you can see here. Hydraulic presses, unfortunately, are too far away to organize a daily trip. We can find these hydraulic presses in Val Sugana, close to Trento. But again, for a daily trip, of course, it's not convenient. So, you see here, after production, you have some slabs of wood, cross of wood. Then, these slabs of wood can be cut, we can cut in these slabs of wood, for example, the openings, or the windows, the doors, and so on, with numerical control machines. Then they are transported, this panel, you can see here, transported with all the openings to the building site. Then they are mounted in the building. See, they are used for both walls and floors, and also for roof elements. Of course, as you can imagine, a crucial role will be given to the connection between these panels. So this huge panel then needs to be connected. You can see here in this quite small here, small connectors. So some angle brackets that are either nailed or screws to the panels to keep all these panels together. So in the end, this construction is made of several panels, and those panels, of course, need to be kept together, otherwise the system will be static and independent. So it will be a lot of, we will discuss later on how we can connect together these panels and how we can calculate the connectors, with screws and nails, in order to ensure that the building is stable under vertical forces and under horizontal forces. So let's try now to understand what are the advantages and disadvantages of this cross-laminated panel. Advantages. Let's think about the isotropic and anisotropic behavior of wood. And let's compare a cross-lab panel with a glue laminated panel. So, in a glue laminated panel, how is the behavior in terms of anisotropy? Which is the best direction and what are the worst directions? So, for example, this is a cross-laminated beam. This is a cross-laminated wall. Where can I expect the best properties? In this direction here, or in the direction perpendicular? In the first. So in the direction of the lamination, this is the best behavior. Same, obviously, in the wall. While instead all the other directions are the weakest direction. Now let's think about cross-lab panel. Where is the best direction for cross-lab panel? Are the same? Or there is one better than the other? No. Let's try to understand why they are not exactly the same. So, consider, for example, this direction here, the direction parallel to the face lamination. compare this direction with the other direction. Why there is a difference between the two, in your opinion?
The number of
The number of layers parallel to the direction. So here we have 3 layers of board parallel to the direction and 2 perpendicular to the direction. Here we have 2 layers board parallel to the direction and 3 perpendicular. So based on this, which one is the best? This? Yes, because we have 3 layers of board parallel to the direction. Why is it better to have 3 layers of board parallel to the direction than 2?
I choose the orientation.
Yes, but why is that? Why is best? You said, right, you said here you have 3 parallel to the direction, and so this is better than this other one. Why is that? Just would like to repeat what we already know. Why is it better to have 3 parallel than 2 parallel? Because anyway, here you have 5 altogether. So you have 5 here, you have 5 there.
There are no fiber, and so more thread.
There are no more fiber parallel to the direction you are considering, right? So since there are more fiber, because in the laminations perpendicular, also there are fibers, but the fibers in this layer here, they are oriented perpendicular. So this means that, for example, if I'm interested in the bending strength, where can I expect to have the larger bending strength? Clearly here, because these layers, the layers parallel to the direction that we are talking about, those layers there are fully resisting. For those layers, I can use the strength of the board parallel to the grain. For the 2 layers intermediate, which strength value should I use when I do the bending verification? It's clear my question. So, when I calculate, suppose that this is subjected to bending in this way. When I calculate the bending resistance, I have to consider that I have 3 layers parallel to the grain. Because of course, the bending moment here is going to induce stresses parallel to the grain in the 3 layers. So I can use the strength, bending strength, parallel to the grain for those 3 layers. For the other 2 layers, which strength should I use in my verification?
Perpendicular.
I should use the bending strength perpendicular to the grain. Okay? Which is
Very low.
very low. So in the end, like you were saying before, in the end, in this direction, my resisting cross-section, roughly speaking, is made by which layer of board? Yeah?
Only the 3 layers.
Only the 3 layers, exactly. So my resisting cross-section, when I check here, is basically only those 3 layers. The other 2, they are there, but in terms of strength, it's like if they were not there. Because they are basically loaded in the wrong direction. Okay? Now, when it comes to look at the other face has 2 layers oriented in the right direction, parallel to this direction, and 3 oriented in the wrong direction. So in this case, again, the resisting cross-section, roughly speaking, will be only those 2 intermediate layers. This explains why in the 2 directions we have a different behavior. Here is the best behavior, 3 resisting layers, and here is the, let's say, a bit worse behavior, 2 layers. Of course, if we compare this with the Lula, it's a completely different situation. In Lula, in this cross-section, what is the resisting cross-section?
Is I.
Yes, but what would be here? If I have to do suppose that here I apply a load, I need to do the verification bending. What would be the resisting cross-section here?
It's the resistance parallel to the grain.
Resistance parallel to the grain, yes, but for which cross-section? What is my resisting cross-section here?
The entire cross-section.
The entire cross-section, okay? Here was not the entire cross-section. Here was which fraction of the cross-section? 3/5. So here the realistic cross-section is 3/5. Here is 100%, everything. Okay? Now, in the other side, we said the realistic cross-section is 2/5. And here, what would be the realistic cross-section? Let's say almost 0, because we are talking about bending in the wrong direction. Bending in the wrong direction, it means compression perpendicular to the ground when we can get something, and tension perpendicular to the ground when we can get nothing, basically. Okay? So in this respect, this material is highly anisotropic, I would say, because there is definitely a best direction, and another one where the strength is almost 0. This one we can regard as a much more isotropic. It's not perfectly isotropic. To be perfectly isotropic, we should have one more layer, 3 on one side and 3 on the other, and then we will be fully isotropic. Instead it's not. Of course, the difference between those two directions are much lower compared to the difference of two directions here in the plural. So in this respect, we can say that cross-tab, it's a much more isotropic material compared to the plural. Okay? It's almost, I would say, almost isotropic in the two directions. Even though we recognize that there is a difference in the two directions. Okay? Clear? Clear to everyone? Okay. Now let's tell me what's up in the third direction. So far we have been talking about two directions in the same plane, in the plane of the structure. We said that one is anisotropic in plane, the other one is in plane isotropic. Now what's happening outside, out of plane? What's the difference between the two cases? Is there a difference?
Is the weakest direction.
Eh?
Is the weakest direction.
Is the weakest direction. For cross-tab, is it the weakest direction?
Yes.
For this one, is the weakest direction? Yes. So in both cases, the third direction is weak. In this respect, there is hardly any difference between blue lab and cross lab. They are both very weak in this direction out of plane. So we could say cross lab is in plane isotropic almost, but remember that out of plane is not isotropic. So out of plane is still a very weak material. Okay? Cross lab. Blue lab is anisotropic. Okay, other advantage. You remember the discussion we had yesterday talking about wood and moisture content. We said that for cross-tab, if there is a moisture content variation, how is this panel going to shrink? This blue lamp panel going to shrink if there is a moisture content variation, for example, reduction of moisture content. In which direction is going to move mostly? This one. Is you want to move more in the red direction or in the blue direction? In the blue direction. So basically, we can expect that the length remains more or less the same. However, the cross-section will shrink. Okay? Now, let's have a look at cross-tab pattern. The same moisture content variation is going to produce all kind of dimensional variations in a cross-tab pattern.
Always in the perpendicular direction
Perpendicular to the plane.
of every layer.
So, in the blue direction, it's going to shrink quite a lot. What about in this direction parallel to phase grade, or the other direction parallel to phase grade? No. Why not? Why is it not going to shrink? Because what we said yesterday is that it's very hard to make to shrink a piece of wood in the direction parallel to the ground. So let's consider first this direction here. In this direction here, there are 3 layers oriented basically those 3 layers are oriented parallel to the grain. So those 3 layers here, under motion content, will basically keep the same angle. However, there are 2 layers oriented in the other direction. So those 2 layers will try to shrink. But they are not free to shrink. Why they are not free to shrink? Because they are glued to the 3 parallel layers that they don't want to shrink. So what is going to happen there? For sure is going to some residual stresses, so some eigenstresses, so autotension will occur for sure. But the end result is that the pan is not going to shrink. Okay? What's happening in the other direction? Is there any difference in the other direction? What's the difference in the other direction? So, the other right direction. There are more panels perpendicular to the grain that would like to shrink, but there are still 2 panels parallel to the grain, 2 layers parallel to the grain that don't want to shrink. So in the end, also in the other direction, the end result is that the length will be more or less constant. So in the end, the cross-lap panel has got better in-plane stability than the glue-lap. Because at least in the plane, in its plane, the cross-lap panel will basically keep the same size. Okay? Other important patterns. Possibility of using non-grade timber thanks to the system lamination effect. What does it mean? It means that, suppose that you have, in this cross-section here, where you have 4 layers of wood oriented in one direction, only 2 layers of wood oriented in the other direction. Okay? Suppose that one of your member has a big knot, a big defect. So the strength of this member here will be much lower. So the influence of this defect in a cross-lap panel is much lower compared to the influence that this defect would have in a cross-laminated timber, in a glue-laminated timber beam. Why? Because thanks to these other panels glued perpendicular to the grain, these forces here can be transferred to the other, thanks to this perpendicular to the grain, let's say, bolts. The forces that cannot be resisted here can be transferred to the other lamination nearby. So basically, stronger sections may compensate weak section neighboring lamination. So individual lamination has less influence on the total load carrying capacity of the member. Okay? And then there is another very important advantage. Now we haven't talked yet about connections, but we have already mentioned that, of course, connecting this member together will be the key action in design. So we will have to make sure that this member can be connected very well to each other. Suppose now that we have a glue-lap panel, so glue-laminated beam, and we need to connect this beam to, for example, a hinge. This connection can be done by drilling a hole and by placing a dowel inside, uno spinotto di acciaio. So we have a hole here, this dowel is going through, and then we subject this panel to tension. Okay, we pull the panel through the dowel and through the panel itself. Okay? Now, once we carry out a test like this, how can we expect that the system is going to fail? Of course, it could be a failure in tension of the glue-lap, could be a failure of the dowel if the dowel is too small. But what is most likely to occur? If the dowel is not small, what is most likely to occur? Is that here you see from the dowel, so this is the glue-lap panel and this is the dowel here. Here we will have a very high concentration of forces. So what would happen here is that if you remember that the fiber are oriented this way, a typical failure would be a shear failure here between the hole and the end of the fiber, along this weak plane, remember the middle lamella, the middle lamella between the fiber. So the typical shear failure would be a shear along those two surfaces here. Or another typical shear failure is a splitting. So basically, this process here will introduce some tensile stresses in the direction perpendicular to the ground. So in this case, when we are going to pull here, we will get, you see, basically splitting along the surface. So basically, we have something like this. Due to the very low strength perpendicular to the ground. So this is the typical failure mode for a grulla member connected to a dowel. Now, let's think about what would happen in the case of a cross-tab panel. So we have the same hole going through the panel, the same dowel, then we apply the tensile force. Is this kind of failure still possible in this case? No. Why is it not possible? Because, exactly, in this case, this kind of failure is possible only, you see, only in these three layers here. 1, 2, and 3. But then in between you have the layer perpendicular. The layer perpendicular is loaded by these tensile stresses parallel to the brain. So parallel to the brain, the strength is much higher compared to the strength that the two outer layers have perpendicular to the brain. So meaning that in this case, this kind of failure cannot occur. It will never occur because the secondary stresses are much lower. These stresses here are much lower compared to those primary stresses. And there are two layers of boards oriented parallel to the direction of those secondary stresses. So if you want, this intermediate layer acts as a sort of reinforcement for the panel. They reinforce and they increase the tensile strength also in the wind direction. So it's very important for the connection, we can avoid this kind of failure here. So this is another huge connection, huge advantage of cross-tab panel compared to glue-laminated timber. In fact, you can see that this is used to avoid some common problems. Suppose that you have a glue-lam beam, you are going to hang something on this glue-lam beam from the bottom side. So you see here, you have a plate, steel plate that goes inside, and some dowels here. Suppose now you hang a very heavy weight, like a very heavy lamp. What is going to happen here? Since you are hanging a load, this is going to induce some secondary stresses, tensile stresses perpendicular to the ground. So the strength here will be very low, and for sure you will get here a crack, splitting, because you are going to subject the wood to tension perpendicular to the brain, where the strength is almost zero. So in the glue-lam beam, to avoid this problem, what we have to do? We have to reinforce the beam. We have to glue, for example, you see some panels outside, in order to be able to keep those secondary stresses. So to drill some, to screw some long screws, to act to resist in tension, the steel of the screw resists in tension. Or you can use cross-tab. If you use cross-tab, you see you don't have any more this problem. Why? Because the secondary stresses this time are taken by those 1, 2, or 3 layers parallel to the brain. So parallel to the secondary stresses. More or less that we were discussing before. So for this reason, sometimes, particularly for very big beams, and where we have holes, notches of hole like this, those notches of hole are other critical points. Because you see, if you have a notch here, very often you have a crack starting here. So with a notch, you need again to put a reinforcement, or with a hole, for example, when you need to go with plants inside, so not plants, with services inside, also here you need to put some reinforcement. Now, with normal glue-lam beam, with cross-laminated beam, instead, this is not needed, because the cross-laminated beam is already reinforced in the direction of the secondary stress, given by the laminations perpendicular to the main direction. disadvantages. Let's say quickly the two disadvantages and then we finish. Or maybe we wait for the next time. No, I think we need for the next time. It's almost better not to rush too much. Okay, on Monday we will start from the disadvantages. I think for the advantages, everything here what we said, because those concepts are quite important, what we have been discussing so far. So we like that they are all clear, because really they justify, they are the key why this material has been used more and more in our country, Europe. So do you have any question about what we have been discussing so far?